So we have 8 times 10 to the negative third moles of our diatomic gas. We know that the pressure is related through this equation, A over V squared, and we're given a value for what A is. We know what the initial volume is, but we want to find what the final volume is after we've added 50 joules of heat to the system. So we look at this and think how pressure and volume are related, and we know that they're related through work. We know that work is negative the integral of pressure with respect to volume. So it's negative the integral from the initial to the final volume of pressure, which we substitute this equation in for, with respect to volume. And once we solve this, we can get this expression for work. Now we know what the initial volume is, we know what A is, we just want to find the final volume. So we're trying to find a way that we can solve for work or something else that will give us what the work would be. We know that the change in delta E thermal is Q plus W. We know Q is 50 joules of heat. We're given this expression for W. And then we also know that delta E thermal is equal to NCV delta T. So since these are all equal to each other, we can set NCV delta T equal to Q plus W. So now substituting this W equation in, we get Q plus A over V final minus A over V initial is equal to NCV delta T. Now we have all these pieces. We have Q, which is the 50 joules. We have A, we're looking for V final. We have V initial. We have the number of moles. We're given CV, but we do need to find delta T. So we need to find the initial and final temperatures. We can do this using PV equals nRT with the initial volume and with the final volume. And then we can solve for the temperature respectively. So we do PV equals nRT, but making sure to substitute A over V squared for P. So we use the 100 centimeters cubed, but we're told that the pressure is related with volume measured in meters and not centimeters, so we want to switch to meters cubed. So we just plug in our numbers, our A, our initial volume squared, our initial volume, our number of moles, our constant, and our initial temperature. And we solve for T initial, and we get 451.26 degrees Kelvin. And now to solve for T final, we do the exact same process, except we use V final. So we have A over V final squared times V final equals nRT final. So we know A, we know that we can simplify this to be all over V final is equal to the number of moles, which we know, the R constant, at the final temperature. So we can solve for the final temperature in terms of V final, which is okay because that's what we're looking for anyway. So we want everything in terms of V final in our equation. So we can move it all to one side and solve for V final. Now if we go back here, we saw that we were going to use Q plus A over V final minus A over V initial equals NCV delta T. We had this, which was the 50 joules. We had A, it was given. This is our unknown. We're given V initial. We're given the number of moles, NCV, and we just found the final and initial temperatures in terms of V final. So we can go ahead and plug that in for delta T. So when we do that, we get NC and then V final minus, or T final minus T initial is equal to Q plus W, and this is the W expression we got from our integral. So plugging in the numbers, we get the number of moles times CV, which is 1.5 times the R constant, times this expression that we got for delta T, is equal to the Q, which is 50 joules, plus the expression we got for work. And we just plugged in our A value and our initial volume in terms of meters. So once we simplify all of this out, we can solve for the final volume, and we know that it's 23.1 centimeters cubed, and that's after converting back to centimeters since our pressure was given to us in centimeters cubed, but we converted to meters. So our final two questions ask us to use our answer from part 1 and try to explain and see how it relates to different things. So we want to see, does the thermal energy increase, decrease, or remain constant, and by how much? So we know that the delta E thermal is equal to Q plus W. So the change in our thermal energy is equal to Q, which was the 50 joules, plus W. And before we had the W in terms of V final, but now that we just solved for that, we can go ahead and put our bounds on our integral and solve for what the work actually is. And once we do the integral with our new bounds, we get that it's 99.87 joules, which is approximately 100 joules. And so we put that back into our delta E equation. We get that it's Q plus W. Q is positive, W is positive. When we add them together, we're going to get a positive number. So since we have a positive number, we know that the delta E thermal, we know that the change in thermal energy is positive, which shows us that it's increasing. So the next question says, how does this relate to temperature? So we know that temperature is the average kinetic energy, and we know that kinetic energy is directly proportional to thermal energy. So if one of them increases, the other one will also increase. So we have E thermal increasing, which means the average kinetic energy increases, which means the temperature increases. And then our final question wants us to think about the work. And it says, do mechanical forces transfer energy in or out of the gas? So since our work is 100 joules, and that's a positive number, we know that it's 100 joules going into our system. And so that means that it's transferring energy, transferring work into our gas.